regarding the assignment question. For beginning and end, kinetic energy is 0. For beginning also and for end also. So when we say K2, it is 0. K1 is 0. 0 minus 0 is 0. W all. mg force is acting downwards throughout the journey. But normal reaction is not acting in a way that it could move with the point of application. Sometimes normal reaction is there, sometimes it's not there. You keep your foot here, it's there, lift it, it's not there. Normal reaction is not moving with your foot. With your shoe, it's not moving. So normal reaction would not be able to do any work. mg, yes. Who else? It could only be internal. If something is going up, mg is acting downwards, work then has to be negative. So the internal work is mgh. Internal work means the work done by the forces inside the body of the boy. If you have any questions, let me know. I suppose no questions. In the last class, we discussed something very important, which is the law of conservation of mechanical energy. You will find its enormous application. Just keep in mind that this law would work when you have only conservative internal forces operating. Conservative internal forces are operating for a system, only then this law would work. That means, okay, now external forces may be present, but they should not do any work if they are present. So either external forces are just not there, they're absent, or if they are there, then they are not doing any work. To repeat, either external forces are just not there, and if they are there, they are not doing any work. And internally, there should be no dissipative force. Internal forces should all be conservative. Then this law would be valid. And this law just says that mechanical energy is conserved, which is the sum of all kinetic energies. All means there may be different components in a system, mass m1, mass m2, mass m3, sum of all potential energies. m1 may be at some height, m2 may be at some height, m3 may be connected to some spring. All should be taken into account. Any clarification if you need about this, let me know, or we proceed with application. Frictionless track. Always remember, when you have dissipative force, consider WET. If no, consider COME. Here, COME. And when you have some height involved, always choose some reference line. Call it GPE baseline, gravitational potential energy baseline. Always, you must do it. A and B are above, but so heights will be positive. But if B, let's say, is somewhere here, then it will be negative. Just apply E1 equal to E2, KE1 plus PE1 equal to KE2 plus PE2. Here your system would be particle and earth system, where observer is on the earth. So as far as earth is concerned, no change will be observed. It will be a game of particles placed at some point, means Ke1 is 0, mg1 half mv square mg 0.5. Just solve for v and see if you are getting root 10 as the answer. If there is any question, let me know. The shape of the track is immaterial. It can be zigzag, etc. Answer won't change. As long as there is no dissipative force, answer won't change. If distance given is 4.9, then most likely G should be taken as 9.8. The wedge is fixed rigidly. The wedge is not going to move. Wedge is not going to move. So no energy will be involved with the wedge. Mass is released from rest. Well, so throughout the journey, there is no dissipation of energy, mechanical energy. So, spring also, no dissipation. You can just consider the very beginning and the very end. Without bothering about intermediate location, just consider the very beginning and the very end. Compression means somewhere here, it might have reached somewhere here. So go for COMA approach. Take block, spring and earth as your system. Take some reference line for GP. So you would have mgh, kinetic is released from rest. Kinetic is 0. Spring is not compressed initially. Spring energy is 0. Finally, GP is 0. And maximum compression means what? Maximum compression means speed will become 0 again. So kinetic is 0. You will just have spring energy finally. That's it. Just solve for x. Take G as 9.8. That may help due to this 4.9. 4.9 into 2 is 9.8. And see if you're getting the answer as 9.8 centimeters. Any questions? Let me know. Now here, right from the beginning till the very end, you can't apply conservation of mechanical energy because there is dissipative force present. So you will have to break this problem into two pieces, A to B and then B to whatever point at which it stops, C let's say. For AB discussion, you would apply COME, for which you can choose some baseline like this one. And then for B to C you would apply wet. Just proceed on your own and then we can discuss if you have any problem. Let me check. The answer I have is 5 meters. And now, if you would like this to be discussed on the board, then raise your hand. All right. A to B. A to B means mgh. H is 1. Kinetic, no. At B it will be kinetic. Now I'm taking this as my baseline for GPE. So potential here will be 0. You can find V if you like, but I don't think you will have to find V. Then what you need to do between B and C is that W all equal to delta K, and W all means gravity cannot do any work. Downward force, horizontal displacement. Gravity cannot do any work. Normal reaction cannot do any work. Vertical force, horizontal displacement. Only friction can do work. F into X minus. Friction is on the left side, X is on the right side. Then final kinetic energy is 0. How far it will move. So it is stopping somewhere. Minus half mv square. That's why I was saying that you would not need to find V. In place of half mv square, you can put this mg into 1. So you would have Fx equal to mg into 1. Frictional force, this is kinetic, so mu times normal reaction. Normal reaction should be mg in this situation. So that is also mg. X is 1 upon mu. Mu is 0.2, 0.5, 5. Any questions? Let me know. Now, while discussing this question, I made use of half kx square. Half kx square we had discussed in the context of work done when spring force is involved. But here I have used it for spring potential energy. I think this needs some elaboration. How do we get spring energy as half kx square? Now, consider spring plus block system. Spring constant is K. Initially, let spring be having natural length. So, no compression, no elongation initially. Some external agent pulls it slowly. And then you have some elongation X. Consider spring as your system. That is the system boundary. During this process, from 0 to x movement, for the spring system, we have W all equal to delta K. One force which is acting on the spring system is by small m. Spring pulls small m by kx force. So spring will be pulled by small m by kx force also. Spring is pulled to the right by kx force. Spring pulls this wall by kx force. So wall will also pull the spring by kx force. On the spring system, there are two forces, kx by small m on the right, kx by this wall on the left side. For a force to do work, force should move along with the point of application. Here, point of application is not moving. So this force by the wall cannot do any work. Yes, here point of application is moving. How much work does this fellow do? This much. Half kx square, right? this half kx square is positive. Force is acting on the right side, displacement is on the right side. Now I considered two external forces, then internal forces. Well, internal force is a spring force. Wext I already considered. One Wext was 0, one Wext was half kx square. Wr means both external and internal. And spring force is conservative. Spring is our system. And we are talking about ideal spring, which is light, no mass of its own. If it has no mass of its own, then final kinetic energy is 0, and so is initial kinetic energy. That means Went is minus half kx square. And this internal means it is conservative internal. It is WCI. But WCI is minus delta U from the definition. So delta U is half kx square. That means whatever is the potential energy at the natural length of the spring, from that value the new potential energy is half kx square more, right? And normally we take potential energy to be 0 when the length, natural length is there, when there is no compression, there is no elongation. Normally we take that as 0. Reference actually can be anything. Reference can be anything. But that's what we do normally in the case of spring. In the case of earth, we keep on changing our reference line, but many times it is the surface of the earth. But we can keep on changing it. We can take it as the surface of the table at which experiment is being performed, etc. The definition of potential energy that we had, that was about change in potential energy. That definition was about change in potential energy. That means you could take any initial potential energy and you could talk change with respect to that. So here when the spring is neither compressed nor elongated, when it has its natural length, then normally we take potential energy as 0. And if that's what we do, then delta U can be written as just U, half kx square. If you have any questions in this, let me know. No questions, I suppose. So I hope now this makes more sense. Finally, initially the spring is not stretched. So U is 0. I mean, spring potential energy is 0. We are choosing it as 0. Now when the spring is compressed, now this derivation that we did was for elongation case. For compression also it is the same story. That can be proved easily. For compression also it is the same, half kx square. So then it is compressed. When it is compressed, then it's half kx square. Any questions? Let me know. when we can talk about a block as a particle, then it makes sense if we are treating block as a particle. Block is there, but it is treated as particle. So we ignore its own dimensions. But what if that is not the case? A building which is having 50 stories, and if this is the reference line, baseline, then what is the gravitational potential energy of the building? When we are handling this situation, then we can't treat it as particle. Or if we can treat it as particle, then what should be the height in MGH formula? When we discuss kinetic energy, then half mv square is the kinetic energy of a particle. And then we say if there is a block system of particles, then as long as everything inside the block is having the same speed, this formula still works. If everybody has the same height, everybody in the building having the same height, not possible. But if all particles of the system have the same height, then this is okay. But in the case of building, that's not going to be happening. So what does one do in this type of situation? How to find the gravitational potential energy for a system of particles, and if everybody does not have the same height? Obviously by integration. So you would go for integration, and you can handle very complicated systems also. Sometimes you can replace the system by a particle. Sometimes when you have a uniform system, say a uniform building you have, uniform, absolutely uniform, like this. Uniform mass distribution everywhere. In that case, center of mass, a point is there which is at the geometrical center. You can replace that by that point. But the general approach is integration approach. So using that approach, you can also handle non-uniform distributions. Maybe something is heavier at the bottom and it becomes lighter and lighter as height increases. Those types of variations, they all can be handled if one does integration. But for uniform situation, geometrical center approach is a very fast approach. Chain type of problem, for example, uniform chain type of problem. If chain is uniform, then you can use this result directly. Say this is a chain, uniform chain, or uniform rope. straight. Length is L. What is the potential energy of the rope if baseline is this? Simple. mg L by 2. Now this rope becomes flat. In that case, its final potential energy will be nearly zero. With respect to this reference line. So you have to know both approaches, integration approach also and replacing by point approach also. there are no dissipative forces, so we can use COMe. This part will have no potential energy because it is at the reference line. This part will have negative potential energy. Let's find out its potential energy. If at y distance, if I take dy element, then its potential energy is mass is dm g y minus, that's du. So its u would be integral of minus gy dm, and there are two variables y and m. This is a uniform chain. Mass per unit length is this. If mass of unit length is that, mass of dy length would be this much. Minus g is out, and dm is m by l dy. Integral y dy. Y goes from 0 to L. 0 to L. So we have minus gm by L, L square by 2, minus mg L square by 2 L. If you have any questions, up to this point, let me know. Negative sign is because it is on the lower side from the baseline. At y distance, there is some dy element with mass dm. Now, initially, small l is how much? 1/3. 1/3 is lying outside. So initially L is 1/3 of L. So initially U is 0, 0 for that part which is at the table, plus minus mg by 2L, L by 3 whole square. That initial situation. Initially kinetic energy is 0. Finally, the total capital L is hanging downwards. In place of L, we should put capital L. I mean, in place of small l, we should put capital L. And there will be some Kf, half mv square. In fact, we want kinetic energy, so I can just call it Kf or K. From COMe, Ui plus Ki, Ki is 0, equal to Uf plus Kf. Now can you find out K? Well, it should not take so long. The answer I have for K is 4/9 mgl. And if you have any questions in this, then let me know. Why we had to integrate? Because we can't treat it as a particle. Heights are changing. So how can we take potential energy straight away? What height will we take if heights are changing for different particles within the system? That's why we have to integrate. Let me know if you have any clarification or any question. All right then. No assignment for today. We stop at this point.